your basic bread and butter regulators that everyone's going to be designing with have, these four main components here: controller, gate driver, power FETs, and then your output filter.
So what does controller do?
How much time do you have? So yeah, it's going to look at your output voltage relative to some reference and decide, hey, we're higher than this reference, so Vout's too high, so we can wait a little bit before we send a pulse. Or it can say, we need more pulses because we're pulling a lot of load current and Vout's starting to sag. In general, that's what they do. And then you can add on all sorts of fancy features, like it watches for over current protection, over voltage protection. You can add telemetry. So if there's an I2C bus or something on here, you can report back temperature, voltage, current levels. It all depends on how sophisticated you want to get. When PWM goes high from the controller, that's telling the gate driver that we have to turn on the upper MOSFET and send a high switch node pulse here to the output voltage so we can add more charge to the output capacitors and keep Vout within regulation.
How this PWM signal builds in the information how these FETs should be controlled, if they should be on or off?
Yeah, so you have your voltage feedback where you're sensing your output voltage and it's coming back to the controller. And you compare that against a reference, and that's what's called your error voltage. And then typically in voltage mode control, which is one of the most common forms of control here, you have a ramp that gets reset on a clocked, every clock pulse, there's a clock running inside your controller, usually set to the switching frequency, and it resets a ramp. And during that clock cycle, you're comparing your error voltage to this ramp. And when your error is higher than the ramp, you send out a pulse, PWM pulse to your gate driver saying, hey, we need more output, more current sent to the output to boost the output voltage.
Okay, and gate driver is changing this PWM signal to the control signals of this FET transistor.
That's correct. Yeah, so PWM coming out of controller is typically, a low current, low drive signal. It would never be able to really switch a MOSFET. And you can get controllers with gate drivers integrated. We'll show a slide on that in a minute. So yeah, PWM is a low current signal. So the gate driver kind of boosts it and then, allows it to drive a FET fast enough where you don't get any turn on problems with it. And then especially if you're doing NMOS upper and lower FETs like I have shown here, you need a special gate drive circuit to turn on the NMOS FET.
What is so special about these signals who are controlling? They need to work very quickly, or?
Yes, yeah. So typically you'll see gate drivers specs, like a 1 amp driver or a 2 amp driver or something like that. It's not necessarily how much current they can pull. It's more of a sign of their pull up and pull down strength on the outputs. They can switch these FETs quickly because if you don't turn them on just right, you can start having what's called shoot through, or VIN. It gets shorted to ground, and that's not good for anybody. Hurts your efficiency, hurts reliability, could potentially blow up your FETs if there's too much shoot through. So your gate driver usually has a few bells and whistles in there to control the timing of the signals to make sure there's no shoot through. And then the upper FET, if you think about an NMOS, just regular transistor, 5 volts on the gate, 0 volts on the source, it turns on, and then vice versa, 0 volts, and it turns off. Well, the upper FET is between VIN and this switch node. So to drive it, you need what's called a bootstrap supply. So you can drive it higher than VIN, drive it higher than VIN when switch node is high, so you can turn it on.
Okay. I didn't know that.
Yes, so that looks something like this here. So, there's a mix of inside here. You have your upper FET, your lower FET. There's the gate driver here. There's that PWM signal. So when switch node is low, you have a diode from the chip supply. So current will flow in here through the diode, and it charges up this bootstrap capacitor.
Oh, that's how you get the higher voltage?
Yes. So you charge up the boot capacitor to, say 5 volts in this case. So PWM, we'll try it this way. Yeah. So if we look in on the chip here, while PWM is low, you have a path here. Your switch node is a ground. So we'll call this ground here. There's your switch node. And then when PWM is high, switch node here goes to VN. So in order to drive that upper FET, you have to make sure that your gate drive signal is at the proper level to turn the FET off and on as needed. So while VWM is low, your boot voltage here charges to VCC on VBOOT. And then when switch node goes high, your ground is lifted up on that driver. That's why it's called a bootstrap supply. And it swings high here to VN plus VCC. So if you're at 12 volts and 5 volts, you'll be at 17 volts up here if your VCC supply is 5 and your switch is at 12. So you have special turn-on considerations for the upper MOSFET, and that just doesn't come in with a PWM signal straight from the controller. So your controller sends the PWM signal to your gate driver. It breaks it out into the upper and lower drive signals where your switch node bounces between ground and VN, and then it gets filtered by this inductor and capacitor and becomes your DC output voltage.
I have another question.
Sure.
So you mentioned this gate driver needs to be able to drive higher currents to control these MOSFETs, and the higher currents are needed to, like, because there is a capacitance or something?
Yes, yeah. So each MOSFET, isn't just an ideal transistor. There's parasitics, resistors, capacitors, inductance of the package and everything. And to handle any kind of significant current, these kind of have to be big FETs, and big FETs have big capacitors on the gate. So the gate capacitance is pretty substantial. It's a couple of nanofarads for a lot of applications. So if you just try to drive that from PWM, it's going to drive that very slowly because this can only output, say a milliamp or two. It's not meant for a high-powered drive signal, and that's what these are for. So if you're trying to switch these FETs, the rise time of a switch node is on the order of a nanosecond, maybe 2. For modern regulators, I mean, if you're switching on one of these integrated FET regulators, we can talk about, you're at 6 megahertz maybe for some of these newer designs. There's just no time to wait for a switch node to go up. You need to bang it quickly from low to high. And that's what this gate driver does, is it ensure you quickly transition from low to high in your switch node pulse here.
So you don't really need like high current to drive the FET itself. You need the high current to be able to switch it quickly to go through the initial capacitance, which will be there.
Correct, yes.
Okay, perfect, I understand. So now the components in the red, what are they doing?
Yes.
Why do we need them?
Yeah, well, if you just leave them out for a second, your switch node here, where these two FETs meet, is called your switch node, and it's banging between ground and VN. So if you just had that, that's a very poor DC voltage, even though it technically meets the definition of it because, it's not centered around 0 volts. So there's some DC offset. So, you can't just send 12 volts to, your little microcontroller or your processor or your op amp, depending on if it's a low voltage one. You have to filter that and just extract the DC portion. So as you switch here between VN and ground, this LC filter will smooth it out into a nice DC voltage with a little bit of ripple on it.
And how do we decide on this inductor and capacitor? Because I think this is like big thing.
Well, we could probably do a video on how to select each of them, but it's a playoff between a couple of things. Board size, what are your efficiency targets, what are your transient responses, and how much inductor current signal you need as well for current sensing, if that's a part of your controller as well. All these things kind of play off of each other. And
so it's not like bigger is better?
Not necessarily, no. For example, if you had a big inductor, inductance-wise, so something big like, say, 10 microhenries, you would have very low DC ripple out here. So you would see, maybe a couple of millivolts on V out. But if you have a very high current transient or, it's a very repetitive transient that's happening very often, your transient response is going to suffer. And this inductor, will kind of limit your response to the whole system. But if you picked a small inductor, like say, 100 nanohenries, you would have a very fast transient response because you could get charged from VN to V out very quickly because the inductor is not limiting your current as much. However, in a DC steady state, you would have a lot more ripple, so you have to size your output capacitor a little bit bigger to account for that.
Okay. So now we know these basic parts of the regulator. What kind of regulators we can have based on these parts?
Sure. So depending on your design goals, you can integrate some portion of all of these controllers here. So you can integrate the controller with the gate driver, the controller with the gate driver and the power MOSFETs, or you can integrate everything all into one package and call that a power module. So there's some pros and cons generally of integrating these parts. So if you went all discrete ICs, controller, gate driver, separate controller, but you integrate the gate driver to the power MOSFETs. If you integrated everything but the passives, and then a module, which sometimes you can get the inductor and the capacitor on a module, but typically just the inductor is integrated in most cases. So all these have pros and cons depending on your design.
Do we have an example for this controller plus gate drive plus FET?
Yeah, absolutely. Let's see. Yes. So something like this here, just pulling up a random data sheet off a DigiKey here. Rohm semiconductor, can take 7 volts in to 28 volts in, 3 amps out, integrated single FET. So here, if you look at just the application circuit, it's very simple. You provide VIN, an enable signal. There's that bootstrap circuit we talked about, and then you need your external inductor and capacitor, and then you connect some feedback components and your compensation network. Very low board space if you're using, small caps and small passives. And then depending on what type of switching frequency you have, the inductor capacitor could take very little space as well. So something like this, if you're looking for high efficiency and low size, solution size, something like this might work. And when I say high efficiency, it's because you have every part separately, your controller, your gate driver, your FETs. Every time you add more trace, more components, you're burning a little bit of power. You're not optimizing everything quite as well as you could compared to Rohm here, whoever the designers are, went ahead and optimized the controller for the gate driver to very specific power FETs. They don't have to worry about what if someone wants more power. They say, this is what we have. This is what we're designing to. So let's design the optimum gate drive circuit to always switch these FETs in the perfect speed and timing to get the best efficiency we can. Whereas if you were to go all discrete, now you have to do all that work.
Okay, I see that there is no frequency selection or something. There is nothing.
No, yeah, this is all just kind of set for you.
So how do you decide on this inductor and capacitor? They will recommend something?
Yeah, so you can scroll through. I'm sure they have application circuits, and usually all data sheets kind of walk you through the process. Or if you start looking through a Buck Design app note, they'll usually have something here. Okay, here we go. So depending on how you want, to configure your regulator, they recommend parts for you.
4.7 microhenry is the inductor.
Correct. Yeah. So if your application was something like this, where they're going 12 or 24 in to 5 out, yeah, this is one of their reference designs here for you to follow. And then typically,
this was a different voltage. Go up. I'm just curious.
Oh yeah, this data sheet covers So this one's 3.3 volts out, so they'll change their resistor divider to set a different output voltage, and here they're recommending just 3.3 microhenries.
Okay.
But usually they give you design equations as well. I mean, every buck converter has the same equation to size your inductor for ripple current.
Okay, let's go back to our presentation.
Sure.
And so let's talk a little bit about this module and about the gate driver plus FETs. So module first. Let's do module first.
Sure. Yep. So a module is going to get you the smallest size because it's integrating that inductor and possibly even some output capacitors. But the downside is they're usually very expensive and you are locked into that module. If you're lucky, the vendor will have a couple different ones that fit the same footprint for different power levels, but you're not going to get Carmen Parisi's module and then switch to Robert Feranic's module very easily. We probably have proprietary footprints because we don't want anyone switching once they buy from us. So your design flexibility is very low.
And this is module. This is not like chip or something.
Yes, the module, yeah.
So I think we have an example.
Yes, we do. So here again, just searching on DigiKey.
Yeah.
Yep, random one on DigiKey. This one's from Murata. You can see it's in this tight little ball grid, or it's not even a ball grid array, whatever they call that package. But it's very small. How small are they today?
And inside, basically, there is PCB and components, probably fitted and correct. And this is just some kind of boxed version.
Correct. Yeah, this is essentially a black box here. So you can see from their application circuit, there's an input voltage, there's an output voltage. You have to supply some output capacitors, and then there's sense lines to monitor V out as well and make sure it's within tolerance. And then a few other pins here because they say it has PMBUS, which is very similar to I2C. And it's part of the system management bus specification, SMBus. It's a subset. So this has probably some telemetry features and a few other little bells and whistles. But
what do you control with this PMBus?
So PMBus is kind of, like I said, a little bell and whistle feature. Not every regulator has it. Not every regulator needs it. And it's a standard. You can search PMBus specification. You can pull it up. And basically, there are a list of registers. And it says if you want to be PMBus compatible, you have to have whatever it is, 24 or so registers available to write to. And it has stuff like vendor ID, like whose part is this, what part is this, you know, what kind of output current can you support, various configuration settings are all in the specification. And then it says, you know, basically you can do whatever you want with it then. So if your regulator, you know, we're talking about integrating features, this regulator here, you don't see, like on our other one we looked at, any compensation components. So this regulator probably lets you adjust compensation through this PMBus. So there's a register to say, you know, adjust the gain of the compensation, you know, place the poles and zeros where you want them. You're doing it through I2C.
Look, maybe there is, there are registers or something listed. I'm just curious what you can set there.
Yeah, let's see. And it might not all be in this data sheet. Maybe they hide some of this stuff. Okay, so here they're talking about the PMBus spec.
Oh, there are some registers.
Here we go. Okay, yeah, this one has quite a few. So yeah, it tells you if there's faults. You can clear faults. Yeah, so you can margin your output voltage high and low. If for whatever reason, you know, you're sitting at 5 volts out and you decide whatever you're powering would work better at 5.1, maybe say. I have no idea what these specs are.
So you can regulate the output voltage?
Yeah, you can change your V out command. You can, maybe not with this specific one, but you can adjust V out on the fly possibly. You can, yeah, set it higher or low. Here you can adjust what your thresholds are for your faults. So your output current, your over temperature. This one monitors V in and tells you if V in is over or under voltaged. Nice. Depending on what you expect. Yeah.
Now I'm curious how much this one cost. Can we find it? What is your tip?
This is $10 in quantities of 100.
I thought it's $1,000.
Yeah, $10 unit. Yeah, no, $10 unit price. Now this is the, you know, available on DigiKey if you wanted to buy 100. I'm sure you could probably negotiate better pricing if you said, you know, I'm Robert Franek, I'd like to buy 10 million of these. They'd probably price it a little less than $10.
But for one piece, it's $12. Oh, it's not so bad actually.
No, if you really needed the size and the optimization, yeah.
64 weeks.
Yeah, and this one here has the option too. As we looked at it, you can put them in parallel for multi-phase operation, which is a feature not all modules have.
So basically, if you would like to get higher current, that's when you use this multi-phase operation, correct?
Correct. Yeah, and it depends. There's no solid threshold between when you need single phase and multi-phase. So say you're doing a high power design, usually, again, it depends on the FETs and all that stuff you pick, the power FETs, but about 20 to 30 amps. Once you start getting above that threshold, maybe you want to look to going 2 phases.
Because the FETs will be more expensive or they will be too big or something.
Yeah, it's harder to find FETs that can do say 40 amps in an efficient package, discretely anyways. Typically that drives you to like a DrMOS chip that we can look at. But yeah, it's hard to find FETs and inductors that can support that kind of current. Those get more expensive, so going to other phases, multi-phases, lowers the cost that way as well too.
Now I'm curious.
There's some other benefits as well to multi-phase.
When you connect these power supplies in parallel, how are you sure they both are actually outputting the same voltage, so currents are not flowing between them?
You just opened a whole rabbit hole. A good portion of my day is spent worrying that currents are not balanced. It's a tricky problem to solve. So we talked about how you control your output voltage. And I pulled up here just from TI, they have this control mode quick reference guide, which isn't even all the ways you can control an output voltage. So some of these modes are out just off the bat when you want to go multi-phase. Voltage mode is gone. Constant on time, it depends on if it's constant on time voltage current mode, but you can see there's a million different control methods. So you would probably use the most common is peak current mode control, where you're sensing the current through either the inductor or one of the lower MOSFETs, and you're monitoring the current. Well, when you go multi-phase mode, you have to monitor all the currents through all the phases. And there's a whole host of ways to do that. And as you monitor the currents, you look to make sure that on average, depending on the topology, that if you're at 100 amps in 4 phases, on average, 25 amps are flowing through each phase.
That's interesting.
Yeah, it becomes a whole separate control loop you have to go ahead and stabilize. And when you have single phase, it's not so bad. Current mode control has been figured out since the 90s or so. Ray Ridley was the one, I think, who put through his PhD paper on how to model current mode control. And then once you add multi-phase, it becomes a whole nother beast. And you can still model it, you can still simulate it, but it gets tricky in practice.
But I guess if you use like a controller or something, then this controller builds in all these features and you just need to connect everything together somehow.
Yes and no. In terms of this particular module here that we looked at, it looks like, yeah, they take care of all the rest. So you see there's this ISUM pin and ISUM pin going here between both controllers. I imagine that has something to do with current balance, but we'd have to sit through and read and see what everything does. If we go to a different example here, so if we go back to our table, and you look for this option here, we'll talk about controller with gate driver plus FETs integrated. So typically, if you're looking for something to Google, it's a driver plus MOSFET package, or if you're in the business, you can call it a DrMOS. And that's
so that's
common.
how you call this chip, correct?
Yeah, your gate driver plus FETs, it's your driver MOS package or DrMOS, and then you have a separate controller. So something like that would be like this part here from TI. So the data sheet is for the 53667, which is the controller. And then you can pair it up. Again, it sends out those PWM signals for each phase. It goes to your driver MOS section, and that has the gate driver and the power FETs in there, and then each phase has their own inductor. So here, the one they're recommending, the CD95490 or CSD95490, they're integrating current sense into each power stage. So it spits out a current signal, and that gets fed back to the controller. And here they integrated the current stage or the current sensing. But if you went with something like this from Fairchild, this is a more standard driver MOS module with no current sensing integrated. So you have to do that externally and feed that to your controller.
Okay. So basically, this is not only MOSFET, but there are some other features and things which helps to make it a little bit easier to connect to controller.
Correct. Yeah. So besides just the PWM signal, it looks like the controller is also sending a disable signal, which is probably used in a sleep state. So if your processor, you close your laptop lid, you throw it in your bag, but you didn't totally power it off, you're still in a very low sleep state. So you want to be on because they don't know, the processor doesn't know when you're going to all of a sudden open it up and need to edit video. So these disable pins are used to put, in various modes of operation to draw more or less current, depending on what the CPU needs. So yeah, there's all sorts of bells and whistles you can add on, but the general functionality is it's the gate driver and your power FETs.
What is on the controller? What pins are on the controller?
So here for this one that we looked at, your VSP, your VSNs, those are your voltage sense pins, and that's monitoring V out. So this has differential voltage sensing, which is what you typically need for processor power. So it monitors the positive end of V out and then the ground over at your load as well.
I remember
too.
even processor itself, the silicon has this VSP and VSN pins, so you will connect these signals directly to processor, and you monitor the voltage directly on die, correct?
Correct. Yeah, if your processor has that in its pin out, yeah, you would connect right up to the rail that you're regulating to, and you'd get the package sense, which is very nice because from a DC standpoint, you take out all the various voltage drops through the PCB and the package, and you make sure on die, if you want 1 volt, you're getting 1 volt there. Not all processors have that. I know some FPGAs don't. Depending on which grade they are, in which case you have to figure out where to place your sense lines on the board for optimum performance. But yeah, all regulators. Do you need to
filter these lines somehow, or how do you route them?
Sometimes you do, sometimes you don't. Sometimes you do, sometimes you don't. It depends. So here, it looks like they're using the PMBUS as well to set the output voltage and compensation, because I don't see a compensation pin. So all that's taken care of, what V out you're at and what compensation you have is all done on chip. So you're setting it through the PMBUS I2C lines. So here you probably don't need any external components, but depending on if you're not doing this, multi-phase processor power application, you might if you're using a different controller from whoever.
What are the other pins?
What does I say? Yeah, this one does have a compensation pin. What do you know? Okay, so there's some external components. A lot of these look like configuration pins. I bet if we scroll to...
Yeah, I guess address, that's like only like...
Pin out, it would probably tell us what those pins are.
I'm just curious,
Yeah. So let's see. There's a pin to set the address on the PMBUS line. There's your compensation pin. Your current sense pins they're receiving. So this is meant to work with... Oh, there are a number of them.
Okay.
Yeah. So this is actually meant to work with just TI power stages because it's expecting a certain current sense signal back. So this, if you bought this controller, you couldn't then just go out and pick whoever's FETs. You'd have to use compatible ones. And then enable, one to set your max current value and your switching frequency. Oh, so this one will report an I'm-on voltage proportional to the current that it's measuring. So if you had some external
analog
or
to digital converter, you can basically see what current you are driving.
Yes, yeah, you can see what current the load is pulling.
Yeah, that's what I mean. Yeah, okay.
If you monitored this I'm-on pin. Yep. Some more config pins for setting threshold levels, as well as some compensation stuff. Your PMBUS lines, the PWM lines for each phase. There's a reset pin. Yeah, so a lot of status stuff here. VR fault indicator, VR hot, which is a thermal flag, I guess, if you have something that's too hot on the system.
Okay, perfect. I think we covered this a lot.
Yes.
So let's go back to our presentation.
Sure.
And what do we have on the next slide, on the next page?
Let's see. So yeah, we kind of touched a little on this as we've worked through so far, but as you select your controller, one of the big things is control scheme. How are you going to control this? What modulation it's called? What kind of modulator are you going to use?
Oh, you already mentioned there are a number of different PWM signals which you can send out, or?
Yes. Well, no, I mean, just in terms of, so, we talked about, okay, we have an error voltage that we compare to a ramp. And when we're bigger, we send out a PWM pulse. That's voltage mode. That's, simple, easy. You can get as complicated as you want. So one of the drawbacks of, voltage mode is you get poor regulation when VIN changes. So if you're going to run off a battery, but then plug in an adapter and switch real fast from, say your 4-volt battery to 12-volt adapter, you get a transient on the input, and that can go all the way through to the output, and you can see a disturbance on V out, even though nothing happened on the load. So that's a problem with voltage mode control. So people fixed it and said, hey, what if we took that ramp and made it proportional to V in? So that's called voltage mode with feed forward. And then...
So then the PWM signal may have different voltages or different levels?
No, your PWM signal will always have a PWM signal, or will always be 0 to 3 volts or 5 volts,
okay.
whatever the thing says. You would just change your on time of the PWM signal with this mode here, with this control mode. So you can see the V peak of the ramp. V peak stays the same. They're just changing the slope of the ramp, and doing that changes your PWM pulse from a fat pulse to a skinny pulse as V in goes high.
Mm-hmm.
But if you need to know your current because you're trying to do current mode control, or you want to have an overcurrent protection function, or for any number of reasons you have to know your output current, well, then you're going to need something like peak current mode control. If you need telemetry, you have to sense the current anyways. So peak current mode control offers a lot of benefits that voltage mode doesn't. Like this inductor capacitor here, I know in any of your other videos, if you've talked about like LC filters, you have a double pole instead of just a single pole roll off in the frequency domain. So current mode control, the way it works, one of the benefits is that double pole goes away, and you don't have to worry about designing your poles and zeros in your loop to account for those. So it's a little bit simpler to control. It has its own drawbacks as well, like implementing the current sense properly is very critical, and you have to add something called slope compensation if your duty cycle gets too high.
So I have a question.
An oscillation, sure.
So this voltage mode control is more focused on stable voltage, and current mode control is more focused on stable current, or what?
No. So yeah, the one thing to keep in mind as you do that is you're still doing a voltage regulator. So at the end of the day, your output voltage will still always be what you're regulating. But how you go about regulating that output voltage can change drastically depending on your control scheme.
Okay, so in the voltage, you monitor the voltage?
Yep, all you monitor is just the voltage. So you have no idea of what the current is doing. You don't know what the in is doing. So you're kind of, operating blind to other parts of the system that may affect how V out is regulated. But if you switch to something like current mode control, you get both current and V in information just due to the nature of having to sense the in.
So you get both information, and then...
Yes.
Oh, okay, I understand now.
So as you know V in and you know the current, you can adjust the duty cycle of your PWM pulse more accurately for all parameters of the system to keep V out within regulation. So it gets a little more complicated, and you can see, again, this is just one document on how to control stuff. There's a million different ways you can control V out. And knowing the pros and cons of all of them is tricky, takes a long time to figure out. But just generally being aware that there are different ways to control V out could dictate some of your choices. And sometimes you don't get to choose, like, whatever this module uses to control V out, that's what you get. It's in the module. You get whatever parameters they allow you to adjust. Same with this integrated FET regulator, whatever control mode they chose, that's available to you.
Okay, I have a question now. What about the frequency of this regulation? Do you have like slide about frequency, or we can just talk about frequency? Because I know some regulators, they give you option to change or use different frequencies. So what are the benefits, or what kind of frequency we would like to use?
Yeah, sure. So one of it comes down to component size. As you switch with a faster frequency, the physical size of the inductor and capacitors that you need generally goes down. So if you're board constrained in terms of area, you'd want a faster switching frequency, just so you can keep your component sizes down and use a small board area. If you're looking for efficiency, depending on how you design your system, switching at a lower frequency for a given set of FETs and inductors typically results in a higher frequencies or a higher efficiency.
What kind of numbers we are talking about? What kind of frequency?
So if you're doing something small, well, let's see, we have examples here for us. Can we search?
It doesn't say. It's top secret.
So this one here is fixed. It's at 400 kilohertz.
400 kilohertz. And is it like a lot or not?
That's about mid-range.
Okay.
I mean, if you're looking at something like, one of your switching power supplies in an adapter or something, those are probably a lot lower at tens of kilohertz for an old school one. But yeah, 400K is a pretty middle of the road frequency. I bet you if we went to, that's the module. Let's see what this guy can do.
So this is the frequency, what is used or how these MOSFETs are switching, and how
yes, yeah, that's
it's
how
the frequency what the
notice.
PWM signal has basically.
Yep. Yeah, so this one switches at 550. Maybe it's selectable elsewhere, but 550 seems to be what they're pushing in their data sheet. This TI one that we looked at has options. Let's see what they are.
Is there something what we need to consider based on like EMC or EMI?
Potentially, yes. But just leaving on the efficiency point, one thing for your FETs so say you've chosen your FETs and now you're trying to decide, do I want to switch at 500 kilohertz or 1 megahertz? One thing you're playing off of here is DC losses versus AC losses. So, your FET resistance here while it's on, maybe 10 milliohms, 1 milliohm, depending on what you're picking in the milliohm range. So you're going to have I squared R losses through the FET. And as you have a lower switching frequency, your on time is going to increase. So you'll have more DC losses, but the energy it takes to charge and discharge the FET here, the gate capacitance, you don't have to switch that as often. So your switching losses go down. But if you were all of a sudden switch those same FETs instead of at 500 kilohertz at a megahertz, well, your DC losses have gone down, but now you're switching them much faster, often on more often. So your AC losses get higher.
And which losses are higher?
Each FET is going to be different. As you switch it differently, you'll find that point of where AC losses dominate DC. It's part of the design process. And even if you pick, the integrated FET option, and all you'd have, some of those have different switch frequencies they can run at. Like I'm sure this one can go to different frequencies as well.
1 megahertz.
This one is optimized for up to 1 megahertz. So once you pick this guy in your design, you have to decide, okay, given my efficiency goals, my inductor I've selected, my area, do I want to switch it to megahertz, or would I look a little better at 750 kilohertz, 400K? It's a design trade-off you have to make as you go through the process. Okay.
And so how this influences the EMC, for example? Is it like more risky to go to higher frequencies?
If you design your PCB properly, no. But as you know, as everyone who watches this channel knows, that's easier said than done. So yeah, a lot of my design tips here as we go through are how to manage the turn on and turn off of your FETs and minimize EMC.
Okay, so let's move to the next slide from the one what we used.
Sure, yeah. So we talked about your control scheme, your switching frequency and stuff like that. As you go through, you also want to select your inductor.
Okay, let's talk about inductor. I'm curious.
Yeah, there's a few key things to keep in mind here. One of them is the core material of the inductor, what's physically made out of. So it's going to be a copper wire that they wind to get your inductance, but then what is that core wrapped around it? And for the buck regulators we're talking about today, there's two main choices. There's usually a ferrite core or a composite core, or powdered core they call it sometimes. And those have different characteristics. So for example, the ferrite core has a lower DCR for a given set of parameters than the composite core, but it also has a hard saturation curve. So if you look at these inductor data sheets, the inductance stays kind of flat with load, and then at some point it starts to roll off as the load current gets too high. And if you have a ferrite core, it has hard saturation, so you're going along and then it falls off a cliff. A composite or powdered core kind of rolls off very gently. So depending on your application, if you're in a very strict current range, you'll never hit that saturation point. Maybe you want to go with a little bit lower DCR and up your efficiency at the risk of, if something were to go wrong, you fall off that cliff, your inductor looks like a dead short, you pull too much current, maybe you blow up the inductor, the output capacitor, your FETs, the load. Hard to say. It's a gamble you're taking on what could be damaged if you saturated your inductor. Whereas if you have a very dynamic environment, different currents, different voltages, everything's changing all the time. A composite inductor with a softer saturation curve might be what you want. That way, if you accidentally go too high, you don't just, short off and shut down your regulator or damage your system.
What about shielded and non-shielded inductor?
Yeah, so shielded versus non-shielded will definitely affect your EMI. Obviously, a shielded inductor will contain the fields, the flux lines a little bit better. And then that's where placement comes in too. Even if you buy a shielded inductor, if you put it on your board wrong, you could hurt your EMI.
What does it mean wrong?
Yes. So if your inductor's marked, look at like this little example I drew here. There's that little dot on some of these inductors that you can buy. That dot should go to the switch node as you place it on the board and you solder it down.
Switch node is where the where the MOSFETs are.
Yeah, where your MOSFETs are switching. Yeah, your switch node. So as you as they build the inductor, you have to start somewhere. So they have their coil wire, and then they wind around, and then there's a coil, on the outside of the inductor. Well, the coil inside the inductor, if you connect it to the switch node, that means the other node of the inductor goes to the out, which is a quiet DC node. And since that's on the outside of the inductor, it shields the noisy switch node from radiating outwards. But if you put the inductor on reversed, all of a sudden your switch node's on the output side, and it can radiate out even with a shielded inductor.
Nice. That's
so
nice.
Something
tip.
to keep
Very
in track
good
of.
tip.
Yes.
Okay. So even like non-shielded inductor still can work well if you place the inductor correctly?
Yes. Yeah. If you design, as you're laying out your board, and I apologize, I don't have a layout we can look at live here. As you place the board, and you can find all sorts of app notes and papers on how to lay out switching regulators. The loop, your FET loop, your switch node, and then this loop here between your inductors, your output capacitor, and then back to the FET are your critical loops. They're high current, high voltage switching. So if you do them poorly, they can, radiate and sing like you wouldn't believe. So keeping these nice and tight and small and compact is your best way to minimize EMI.
Okay, I think you have it somewhere in the next slide. So let's move to inductor, physical size and value.
That's the last thing I want to hype on that real quick. Don't forget the Z-axis when you size your inductor. So you have your XY footprint, and then inductors also come in different thicknesses. So for a 5 millimeter by 5 millimeter inductor, do you need 1 millimeter height, 2 millimeter height? Can you go with 10 millimeters? And that's where to break from the data sheet as well. If you're picking inductors, or you're picking a regulator that's spec'd for a laptop, well, these days laptops are all paper thin. You can't stick a thick inductor in there. But if you're just doing an open top board, like a Raspberry Pi or an Arduino board or something that's open to the air, well, you have a lot more play in what kind of inductor you can use. So if you get a taller inductor, typically you get better efficiency because you have more core in the inductor and you have lower core loss. So it's something where if you just follow the data sheet and say, oh, they recommend inductor 1, 2, 3, 4 from whatever vendor, I'll throw that in there, even though it's, for your application, it's totally wrong. If you have that extra height you can squeeze out an extra little bit of efficiency from your regulator that you might not otherwise
again,
get.
The very nice tip. I like it.
Yes. Yeah, don't limit yourself if you don't have to. And then,
this is
the other
interesting topic. People always keep talking about capacitors.
I could talk about this all day. Yes, absolutely.
So low ESR or zero ESR or...
Well, if you watch any videos by Steve Sandler, he's going to say definitely not zero ESR. He's designing to a flat impedance, which is a whole nother topic that I have to deal with on my day-to-day. But capacitors, there's a few things to think of for capacitors. One big one to look at too is all ceramic capacitors. So as you go on DigiKey, you can see tantalum capacitors that are surface mount and the aluminum electrolytics that are cans. Those are typically called bulk capacitors because you can get a lot of capacitance in a small size relative to a ceramic, which is nice and small and can't really get a whole bunch of capacitance in there. And a lot of people want to go to all ceramic C out because you can get a nice small board footprint, low height. but you got to watch with all ceramic because some control schemes, depending on what you're doing, don't support this. So there's something called V squared control or constant on time control. It's sort of in the middle between voltage and current mode control. That's a whole nother thing. But
and then you don't want to use ceramic capacitor, output capacitor.
You have to read the data sheet very carefully in that case, because early V squared control required a bulk capacitor and a certain amount of ESR. And typically ceramics, if a bulk capacitor is 10 milliohms, 100 milliohms of ESR, your ceramics are going to be 10 milliohms or below in a lot of cases. So like something like early V squared control requires a certain ESR because it needs that ESR signal on the ripple to regulate the output voltage. And you can have an unstable system if you went all ceramic and didn't have that on there. So it's something you have to look at in your data sheet for the controller very carefully and make sure it's supported.
Now, tricky question. So, but when you place this bulk capacitor and then after the bulk capacitor you place ceramic capacitors, then isn't it going to change the parameters anyway of the power rail?
Yes and no. That's a whole complicated topic. Yeah, and typically if you're looking, it depends on what perspective you're looking at the impedances from. Yeah, so if you're looking from the load back towards all the capacitors, as you have all those capacitors in parallel, you see one impedance. As you look from the regulator out, you'll see a different impedance. And typically though, at low frequencies, like your regulator is only going to be regulating, the bandwidth that can control is roughly, the rule of thumb is about 1/10 of the switching frequency as a very general rule of thumb. So if you have a 500 kilohertz regulator, your loop bandwidth control loop is going to be about 50 kilohertz, give or take. So where the bulk capacitor comes into play is that ESR affects the control loop down in that low frequency range, whereas you won't even see the high frequency ceramics when you're looking at it from the regulator's perspective.
Nice explanation. I like it.
Yes. So it all depends on what regulator you're using. If it expects that ESR to be there, do you have to account for it during compensation? Is it required in terms of something like constant on time or V squared control? All stuff that plays into your design.
I think we should also explain bulk capacitors. So what can we use, like I don't know, tantalum capacitors or?
Yeah, tantalum, aluminum polymer, electrolytics, all of those would fall under the bulk capacitance range. And then anything ceramic, as they say in the name, is you go to DigiKey and look for capacitors. You can see, so anything here like your aluminum polymer caps, electrolytic, tantalum polymer, those would all be bulk capacitors. And then ceramic capacitors are their whole own category.
Okay. What else is here? What value? The biggest.
Absolutely, just slap the biggest capacitor on there that you can, and go from there.
Really? I was just kidding, because sometimes.
Oh no, yeah. You don't want it's a little bit of an art. I mean, there's a lot of math and optimization you can do to it, but also knowing, how to size it is a little bit of an art. And pricing plays into it and all that, whatnot. But use the data sheet for guidance. There are some equations. I will call this out. I have it at the bottom of my frequency or my presentation here. So this paper here that TI put out back in the early 2000s, under the hood of low voltage DC to DC converters, fantastic paper. Brian Lynch, I've met him a few times when I worked at TI back in the day. He's a really great guy. One of the smartest guys you'll ever meet. Walks you through a step-by-step design process of designing a buck regulator and all the things that go into it, from gate driver to output capacitors. It's just phenomenal. I highly recommend going through this. And here he's got equations for how to set the output capacitor. And there's pros and cons to this equation. If you're doing some real high performance designs, these kind of fall apart a little bit, but just for your bread and butter designs out there, if you're not doing anything too demanding, no extremely fast load transients or giant steps, these equations will get you a good way to a full design.
So basically, you need to consider like output voltage, current, inductor. That's everything what plays the role in.
Yeah, your step size, and then you've done videos on output capacitor layout, and different footprints give you different inductance and how effective the footprints are. If you pay no attention to how you put the output capacitors down there, even though on paper you have enough capacitance, placing them on your board wrong with a poor layout can hurt the effectiveness of the capacitors, and then you need more all of a sudden. So instead of taking your 100 mic bulk capacitor, you have to go find a 200 mic because there's a poor layout.
So, and is it wrong if you put there more capacitance as it is required?
It's not wrong. I mean, the regulator will still function, but you're paying for that capacitance.
It's just more expensive.
Yeah, more expensive.
Unnecessarily expensive.
Exactly. Yeah, you've over-designed your system. Yeah. What's the expression? Anybody can build a bridge. It takes an engineer to build a bridge that barely stands. So you have to know when to use just enough capacitance and not more. Yeah, and that's where simulation comes into play, testing it on an eval board that you get from a vendor before you do your own design. And if you have access to like Cadence or Hyperlinks or ADS that you've used in your videos, that also helps a lot too in terms of optimizing the placement and the layout and everything.
And I've seen you have there also input capacitor.
Yes. Where is that one now?
Many people forget about this, and I've done some videos with Min Zhang about EMC and how important it is to place these input capacitors correctly.
Yes. Yeah, I have another slide on that specifically as well too. So yeah, on the output side of things, because of buck regulator steps, a high voltage down to a low voltage, the output voltage is low by definition. So derating on the output capacitors, if you look at any of the capacitor curves, you get so much capacitance, and then as you apply DC voltage, it rolls off. If you're doing a low voltage design, 1 volt out, 2 volts out, the capacitors derate, and you have to account for it, but it's not as big of a factor as on the input side of things. So if you have 12 volts, across a 1 mic capacitor, depending on the size of the capacitor, the dielectric, that capacitance could go from 1 microfarad down to almost nothing, in which case you don't actually have any capacitance on your design, and you could suffer. You could see too much ripple on VIN and ruin your design. So you have to account for DC bias, and then size appropriately for that. So if your 1 mic cap cuts in half to a half a microfarad, well, now you need 2 to keep your DC ripple in check. And then the manufacturers of these capacitors also tell you how much ripple current the capacitors can handle too, because as you switch the FETs off and on, the VIN current bangs around quite a bit. And you don't want to violate that spec, or your capacitors could heat up and fail as well too.
So basically, what voltage this capacitor should be rated on? If input voltage is 12 volts, then you can't really use 12 volt capacitors, correct?
Caps, no, yeah, and that plays into what kind of design you're doing. I mean, a 16 volt rated capacitor could be fine if you're going for cheap consumer goods or whatever. But if you need like a high reliability, we got to make sure this thing will never fail. Maybe you'll go up to a 25 volt cap or something.
Like double, yeah.
Yeah, about double. It depends on how much, how close to the edge you want to be.
Do you need to consider this also on the output capacitors?
You do, yes, but not necessarily to the extent you do on the input side of things, because the output voltage is lower. So for a given capacitor,
it should not, on 5 volt rail there should not be 12 volts.
Yeah, ideally, but no, you will still see derating on like a 5 volt rail. So if you're going to use a very small 402 capacitor or something on that, well, that's going to really derate under 5 volts, whereas like a bigger 1206 1210 size package is not going to derate as much. So package size really helps.
Derate means the real capacitance is not going to be, I don't know, 10 microfarad, but it's going to be 3 microfarad.
Exactly. Yeah. For a bigger physical size capacitor like a 1210, it's not going to derate as much as a small 0402. So yeah, the size of your capacitors also dictates to how much you have to worry about derating.
Yeah. Once I've done video on this topic, so I think everyone who is interested to know a little bit more, they need to check the characteristic. Can we open characteristic of a capacitor? I can just show it.
Sure. Here, we're still on DigiKey. Why am I going there?
So everyone knows what we are talking about.
Yes. Good point.
But when you see these reference schematics, I guess they already considered this degradation. No, like if they say use 10 microfarad capacitor, they already know they only need 3.
You would hope they do.
Okay.
It depends. Yeah, that comes into trusting the reference designs put out there by apps engineers like me. So I can say that yes, I do, but I can't vouch for all of them out there.
Okay.
So here's what we're talking about here for the capacitance. I have no idea which capacitor this is. It's just when we pulled up on Barada's sim surfing tool. All of the big vendors, I've used a similar type of tool on their websites as well. You can get all this data for the capacitors, and you can just slide over and see, okay, this is a 100 microfarad capacitor, it looks like. If I apply 6 volts to it, all of a sudden, nope, it drops 84%. So your 100 mic capital, it looks like
16.
15. Yeah, 15, 16
yeah.
Microfarads. Whereas if you're down here at a volt, you're only down 20%, 15, 20%. So you have 85 microfarads. That's definitely going to affect your design.
So this is probably most important. If you calculate your required capacitance, then you should not forget about this.
Yes, absolutely. As you go through the data sheet and the app notes and you go through the design equations and say, I need 100 microfarads of capacitance to keep my ripple in check or for my transient response or whatever it is. You should then go ahead and say, okay, I have X amount of size on my board. So that means I have to use 0603 caps. 5 volts out is kind of a lot for an 0603 cap. What's the derating look like? Am I going to actually have that much capacitance?
Perfect.
And if you're running in a simulator, go ahead and adjust the capacitor yourself there to account for derating. As it has the 100 microfarad nominal value for this cap, just go ahead and knock it down to 85, 80, 60, see what happens. Does your design go unstable? Are you still within your specs? Do your homework and really study to make sure this is something you have to worry about.
Okay, you can go back. Okay, I think that's everything about capacitors.
Yep. Yes. Okay. So we're talking about selection. Now let's go into, as you actually do your layout and your schematics, talk about some stuff that you should take into account as well. So debugging hooks that you might want to incorporate, gate resistors. So this is in the case that you have a gate driver chip either integrated into the controller or it's its own IC. You can have resistors between your upper gate drive signal and your lower gate drive signal to the FET. And what they do is they control the turn on and turn off the power FETs, how fast they'll turn off and on. And you can use a single resistor like I showed here for the upper FET, which is cheap, but it affects the rise and fall edges equally. Or you can get fancy and kind of put 2 diodes here and have a separate rise and fall resistor and control the slopes independently.
Wow.
But that comes at cost and more board area. This is one of those things where if you go all discrete, this is a choice you have to make. Whereas if you get the gate driver integrated with the FETs, that's already been taken care of for you, and all this is optimally set.
Okay, that's what that was my question. Like a gate driver should be probably controlling the edges by itself correctly, no?
Yes, but the gate driver, because you can want to put that resistor in the silicon itself because you don't know what kind of FET you're trying to drive. So you want this.
It depends.
This
okay,
signal,
it depends on the FET what you choose.
Absolutely, yeah. So you want this signal coming out of the driver to be as fast of an edge as you can, and then you have to adjust it to the FETs that you've selected because the maker of whatever gate driver chip doesn't know what you're going to put at the other end of it. As
so
a load.
how would you like to change it? What would be like optimum shape of the edge?
It's going to be very application dependent, and we'll get in that more as we go through. But you want to make sure that when you turn your FETs off and on, that you're not having overlap between these upper and lower gate drive signals. Because
That's
if they're
what you
both
already
high at the
mentioned, like
same
there is no
time,
short circuit from V in to ground, for example.
exactly, yes. You want to avoid shoot through. And then you also, so okay, maybe we delay the signals a little bit, but you don't want to delay the signals too much because then you have a lot of time where the switch node isn't conducting. It's called dead time.
So basically, like it's floating.
Yes. Yeah, it's floating, but it's not, because then the inductor forces you to pull current through the low side FET body diode that's there.
Oh yeah.
And the body diode pull is way less efficient than the FET itself. So if you have too much dead time, you're hurting your efficiency, even though you have no shoot through. So yeah, just a bunch of design choices you have to make if you go the all discrete route.
This is good to know, because I've seen this RGATE resistor in some schematics, and I really didn't really think too much about how is it used. So now I know. I think in the note somewhere I read you can start with small values. Maybe it's on different.
These ones here, yeah. I mean, because the layout too is going to affect the values as well. You know, how much capacitance there is on this line, and how well your traces are routed too. So yeah, I would start, if you're confident in your design, you're reusing it from an earlier design as well. Keep those, you know, small 0 ohms, maybe 1 ohm, and then probe your signals at the FET to make sure everything is looking good, and then make sure your switch node is what you expect to before you go ahead and remove them entirely. Whereas if all of a sudden you're seeing shoot through and other problems with your FETs, then you go ahead and start walking them up. And there's calculations too, plenty of app notes on how to size a resistor for a given FET size.
So when you mentioned this layout, what would be like optimum way to route this UG to the gate of the transistor? White track, thin track?
Well, definitely in terms of placement, you want to keep your gate driver close to your FETs. You know, we talked about switch node having EMI because it's a high current signal. Well, we mentioned gate drivers are usually spec'd in terms of drive strength as well. So you're trying to slew the gate capacitance of both these FETs very quickly. So you can also get EMI from your upper and lower gate signals as well. So you want to keep that path short too, just so it doesn't radiate out. So short, and then you're not going to use like a plane, like a voltage plane, but you don't want minimum width traces at 4 or 5 mils, whatever your PCB house can do. I typically route my gate tracks, you know, about 12 to 20 mils, depending on the design. So fat.
So
got to be able to carry that current.
So lower the resistance, but don't make the capacitance too big.
Yes, yeah. So what happens, if you make the, and I've seen this on a few designs, is if you make the, you know, say you route them with planes, an upper gate plane and a lower gate plane. Well, now you've just made a big capacitor. So you've added that capacitance on top of your FET capacitance, and that just causes more problems. So yeah, a fat trace, you know, something in like the 15 mil range, give or take, is usually pretty good for those. And I say put the debugging hooks on there, the gate resistors, even if you don't end up needing them. You know, pull them off, I guess, maybe on the final prototype stage if you think you can get away with it, but you definitely don't want to need these signals and then have to cut trace with an X-Acto knife and try and layer them in ad hoc. That's no.
Okay.
That's
what about CBOOT?
Yes. So the next one, we'll just jump to that one here. Say you get your DrMOS package, and we looked at this TI design here. So we looked here, so they integrated the driver and the MOSFETs. There's still this boot path here, and same on the standard one here. There's a boot pin,
it's
and they also show
with
this
the
boot resistor as well. Yes. So if you picked something where the FETs are integrated, you don't have access to the gate drive signals, so they're short, because you can't get much shorter than on the same IC. And the timing of it has been taken care of by the IC vendor to ensure there's no shoot through, you have optimum dead time. But you're still seeing, because of layout or whatever reason, ringing on the phase node or poor EMI. You might need a boot resistor here, which is always something you can put in as well, external to the part. They don't show it here on the TI one, but they do for this Fairchild part. That boot resistor is in place. So again, you want to keep the boot phase path very short, because as we note here, the bootstrap supply switches on the boot pin. You'll see it at VCC, but then it goes to VIN plus VBOOT, VIN plus VCC, sorry, when the switch node is high in order to keep the gate driver on while the upper FET is on. So you're swinging a lot of voltage very quickly, also a path for EMI and noise to radiate from your design. So you want to keep the CBOOT, RBOOT path very tight too. And I think they show that in a layout example.
But the values will be basically specified in datasheet, and you don't need to like worry about values.
Correct, to an extent. Okay, so they do show it here in this application schematic on the TI part. They do show a placeholder for the resistor as 0 ohms. And then they're using 0.1 mic. And this is typical in the designs I've seen. A 0.1, maybe 0.2 microfarad capacitor is usually correct. So you want to have enough capacitance where you can hold the boot voltage high while the upper FET is on and keep the FET fully on. You want boot to collapse while only CBOOT is providing the charge. But you don't want too much capacitance, because when switch is low and this diode is biased and VCC is charging up the capacitor, too much capacitance needs more current to charge. You could strain your VCC supply. You could burn out that boot diode. You might not charge up in time before switch node goes high again. So yeah, following the datasheet recommendations for CBOOT is a good idea. And then the RBOOT placeholder is very good as well. I don't know too many designs I've seen that leave it out entirely. So yeah, what that does is it limits the current as CBOOT provides the power for the gate driver itself. You know, it's a current limiting resistor basically. And it can help reduce shoot through EMI, definitely EMI. And then start with a small value. 0 ohms is the placeholder they have in that data sheet we looked at. Maybe 1 ohm or something. If you decide you need it, definitely start small and work your way up. If you put on, say, 100 ohms, that's huge for a boot resistor. Your upper FET might turn on so slowly that you blow it up. So start small, walk your way up. Typically, you'll see kind of like a little parabola if you're looking at, say, efficiency. And there's too much ringing. You're wasting all this power ringing out instead of supplying it to the load, or there's shoot through. Use RBOOT, you'll see efficiency start to boost a little bit. Not a lot. You're not going to go from like 90 to 100% efficient, but maybe you get a 0.5%, 1/4%, something like that, as you walk the boot resistor up, and then you'll go from that 0.5% boost back down. It kind of is like a parabola shape, so you'll know when you found the optimum value through trial and error.
Now I have a question. I know
Yes.
it is somewhere in your slides, but how can you measure this precisely? Because I think once you touch with your probe somewhere, and then it's going to add some capacitance, and it's going to a little bit influence the shape, plus all the inductance and
yeah, so probing plays a very important part in making sure your regulator works when you get to the validation stage. Where I do have a slide on that. Yes. So for probing techniques, you always want a very tight ground connection. These long, giant ground clips that come with the probes, throw them away. If you're just doing like the very first power up of a board and you want to make sure there are signals present, sure, go ahead and just tap various nodes. And yes, we're seeing a rising edge on their upper gate pulse. Yes, phase is there. Yes, V out is roughly 5 volts. Totally fine for that. If you're doing serious validation work, go ahead and get rid of that. Don't use those ground clips whenever possible. Use the spring clip or solder, your own little wire. I've made it myself, where you just wrap a little bit of wire around the ground of the probe and solder it, to the ground of a capacitor, right where you're trying to measure, and then you put your tip wherever you have to for the signal of interest. Keep that ground path very short to get the best possible signal.
So if it's long, what will change in what you measure? You will see
the big one is noise and ringing. So if you're looking at ringing on your gate drive signals or your switch node with that long ground lead, who knows what you're going to get. You might have perfectly fine ringing in actuality, but if you ground way away from your chip with a long ground lead, you don't know what you're picking up and what's going into your scope there. You could see tons of extra ringing that's not actually there in the circuit, causing you to add extra components to slow things down, possibly hurting your efficiency. It's costing you design time as you work through the problem. And then, on your output ripple, if you have a certain spec, you know, you're going to see all that extra high frequency noise coupling in, and it's just going to look awful on your scope.
Do you need to also
that,
be careful about what probe you use? Like standard probe, is it like okay, or you need like special probes?
So the passive probes are pretty good for a lot of the general characterization. And I mean, you know, it also depends on your budget too. If it's you and me sitting at home, differential probes, power rail probes, all these fancy ones get very expensive. So you kind of got to work with what you have. But yes, having a variety of probes available is helpful. So, you know, your passive probe, you have your signal and ground, which has to be ground because that's connected to ground on the scope. But, you know, if we go back to here, say you want to measure just across the boot capacitor, well, that's at, you know, VN or VCC, which could be about 5 volts or so, and then it jumps up to VN plus VCC, say that's 23 volts. Trying to measure just that with a passive probe and make sure you're not seeing any, you know, decline or ripple or whatever while it's on is pretty tricky. So you might want to switch to a differential probe and put that right across the boot capacitor. And that comes with its own set of challenges you have to work through. So one is look at the data sheet for whatever diff probe you have. Make sure you're not exceeding the common mode range. So that's what DC voltage can you apply between the 2 pins of the diff probe. I've seen some go as low as 8 volts, and I've seen some go, you know, 50, 60 volts, depending. And then there's special high voltage diff probes for very different applications. But for what you'd use on like a buck regulator, you know, make sure you're looking at a proper common mode range for the signal you're looking at. So if you're trying to measure VN with a diff probe and you exceed the common mode range, you're going to get funny results on your scope. If you
So
look at this,
you may not even know your signal is actually higher than the range of the probe, and you will still be able to measure it, but the result will not be correct.
A little bit of both. So what's Dr. Begotten say? You know, don't run a simulation or take a measurement without first expecting your results. You know, thinking of your results ahead of time. So yeah, just do some quick math. You know, is boot to switch? It's going to go from, you know, 5 volts to 23 volts or something. Say, okay, let's take a look at my diff probe. Can it handle a 20 volt common mode range? Yes, it can. I can look at that. So something I've seen in the lab is if you have the wrong diff probe, it looks like your boot voltage collapses. So you're expecting 5 volts across that capacitor all the time, but you're measuring, you know, 2 volts or 1 volt you look and your diff probe has the wrong common mode range, and you go, oh, I use the one that has the higher bandwidth that can go to 2 gigahertz. That one can only have 10 volts across it, and I'm measuring 20 volts DC. Okay, switch it out for the lower bandwidth one that can have the higher. Boop. Okay, it's exactly what I expect.
Okay.
So yeah, in that case, you'd be wondering, well, how the heck then is the switch node even rising if there's no voltage on the boot voltage to drive the FET? And then that's where you start thinking, okay, what did I do wrong? Is it a setup issue? Is there something actually going on here? So yeah, look at your diff probe. Make sure you have the common mode range. And then for ripple and other low-level signals, like if you have one of those current mode designs or multi-phase designs and you want to check to make sure your current signals look good, they're typically low-level signals. Look at the data sheet of the diff probe too and get the noise floor. What kind of noise can you expect on the probe? Because if you're trying to only measure a 10 millivolt signal, but there's 3 millivolts of noise, that's 30%. So your signal could look noisier than it actually is. So something else to keep in mind as you're looking at waveforms on the scope.
Very good tip.
Yes. And then for stuff like ripple, a power rail probe could be what you want to use. And you could buy these for thousands of dollars. They're wonderful probes when used right. But also LaCroix is very nice and has a little app note here on how to build your own with a piece of coax cable and a 50 ohm resistor. So this gives you a nice clean signal terminated properly to show, so here we were talking about what can you see using a passive probe with a long lead or, 1 mega ohm input on your oscilloscope not terminated properly. You can see all this extra ringing, but if you use a proper probe, look, it's actually just a small amount of overshoot. So it's stuff like that where if you probe wrong, you can see all these artifacts that aren't actually there.
Very important.
Yes. Yeah. Probing is a huge one. A lot of times I'll get request for help from the field or a customer or whatever, and they'll show these waveforms, and depending on what they're saying is hey, our output voltage ripple is out of spec, and then you look and you see all this kind of ringing, and you're like, okay, before we dive into something wrong with the regulator, where are you measuring from? What are you using to measure?
Exactly.
And work through from simple techniques down to, yes, okay, we have a problem. Let's look at your schematics and solve it. Yeah.
I've seen this many times. I keep saying this because on forum I receive this kind of questions like, I have this kind of, I measured this kind of signal. What's wrong? But how did you measure this signal? Like, what did you use? Like, maybe signal is perfectly fine. Just maybe you are measuring it wrong or something. I don't know.
Yes. Yeah, it could be that. And, something that comes up too, here's a tip I don't have in my slides. As you engage with vendors and try and get help, too much information is definitely better than not enough information, in my opinion. Nothing's worse than getting a scope capture, probed
exactly
correctly, incorrectly, whatever, and it's zoomed out. You can't see anything, and they just say,
"This is what I have on my scope." What's the problem?
Yes, my regulator shut down. What V in? What V out? What were you expecting to see? What mode of operation are you in? It's better, in my opinion, to feed an apps engineer or somebody more data and let them say, okay, that doesn't matter, that doesn't matter, that doesn't matter. They're the expert in whatever chip you're looking at. They can quickly say, okay, that's irrelevant to what we're seeing. Oh, this is interesting. That might play into it, and ask follow-up questions. But yeah, just here's a scope capture. Something's broken. You'll get help eventually. You're just taking a lot longer.
Yeah. Okay, we can go back.
Sure. Yeah, so a different hook here you can put into your design, if we're talking about EMI specifically, is a phase snubber. So just using, let's go back to that LaCroix app note. Let's assume all that ringing is real for a minute, and that's what you see on your switch node. Well, that's really ugly. That's going to fail EMI. Depending on the peak of that voltage, you could be outside the data sheet limits for the FET. So you want to get that under control. For whatever reason, you don't want to use these other methods, or you have used these other methods, but you need something else. This snubber resistor and capacitor help kind of dampen that ringing out. So typically I'll see designs, leave those not populated to start, and then if they run into issues, they have the hooks there already in place to populate them and keep phase ringing under control. And you size your capacitor appropriately. There's a few app notes I think I have at the back of my thing on how to go through and pick your capacitor value and your resistor value to dampen out those ringings. So when you're putting these on your board, though, I will say these are kind of a secondary concern after your FETs, your inductor, your input capacitance, your output capacitance, because if you've laid those out correctly, the ringing is going to be under control. And it's not going to be, especially if you have something like the DrMOS package where your gate driver is already built in, so you don't have to worry about that. If you lay out your input caps, your planes, all that stuff really nice and tight, you probably won't even need this.
If you need it, probably there is problem.
Yes, exactly. So place the main components, the FETs, the inductor, the capacitors really well, input decoupling. Do a good layout on those, and you probably won't even need this. Once you get those tucked in, don't put these components all the way across the board, inches away possibly from your switch node, but where you fit them in, okay, hey, I have everything nice and neat on the top side. If there's room to fit them on the top side, great. If you have to throw these two on the bottom of the board compared to the other ones, that'll do too. It's definitely a secondary concern, I would say.
Okay.
A good design will invalidate those, but if you need it, then tacking on these at the end of a design is a lot harder than just accounting for them to begin with. Footprints are free.
Yeah.
So something else too to think about is an extra MLCC on VN. So I know we said we were talking about accounting for derating on your capacitors too. This, you should account for derating as well, but this isn't going to be one of your main input capacitors. This is kind of a secondary cap. So I realize now I drew the picture a little off, but say for whatever reason the pinout was a lot smaller, something like this, and maybe sloped, so you couldn't get your main capacitors in nice and tight, or for whatever reason they got to be located a little bit farther away. still sneak in a capacitor as close as you can get to these to your input caps, or to the input of your FETs, just to decouple nice and tight as close as you can possibly get to the package. And that can help lower phase ringing as well if you've picked the right values, and just give you that little extra bit of performance that you might need to hit your design specs.
Okay, I understand. So basically, if you can't place it, the input capacitor very close to the pins, then you can use extra additional smaller capacitor which will fit closer. Yeah, it doesn't have to be, or it will not be maybe as big as you need, but it still will be helpful.
Yes, yeah, any decoupling there, because really what you're trying to do is control the inductance then in that case. And the smaller package capacitor will have a lower inductance and allow you a little bit more high frequency decoupling if for whatever reason you can't get your nice big wide planes like I've drawn here, or a bigger capacitor nice and close. So for whatever reason you just can't get everything super nice and tight, then at least really try to squeak in a small decoupling just for that initial burst of energy right when the switch node fires, just to have something there to decouple it.
Because if we don't place these capacitors there, then this will just spread all over the board, or maybe even cables, and that's what will cause EMC problems.
Potentially, yeah, or not even looking at EMC too. If you're just trying to keep your phase node from ringing too much, and keep within the data sheet limits, a board spin is a lot of money. But
okay,
if you
because then
just...
because then you will not get proper input signal if they are not there. Or voltage,
potentially,
input voltage. That's what I mean.
Yeah. If your input voltage collapses a little bit right when phase fires, it's going to throw off, the gate driver. It's going to throw off, the performance of the FETs. So just that little bit of extra decoupling. If for whatever reason you can't get the perfect layout the way you want it, you have to make some trade off for something else. A small MLCC right there is.
Okay, I understand, because basically your controller is some kind of expecting specific input voltage. That's how it calculates basically how long the transistor should be on and off. And if suddenly the input voltage will drop, then basically it will not, the output will not be what controller wanted to have.
Yeah, exactly. You could throw off the PWM timing. You could, throw off the turn-on characteristics of the FET, and just start seeing really weird stuff. So yeah, good input decoupling is very important. And this is kind of just your last little, all right, I had to make trade-offs, but here's something I can do to kind of mitigate, some of the performance hits.
Okay.
Just getting a nice small package as close as you can in there.
Okay, I understand.
Yep.
We went through this one.
So yeah, we talked about the probing techniques. So yeah, when you're going through, let's assume you have good probes, good layout, whatever, all that jazz. The phase node, the switch node, is one of the most important nodes of the regulator. I mean, yes, probe all your signals, do your homework during validation to ensure everything's working, but the phase node is just critical. I can't stress that enough. It can tell you a lot about how your system's performing, from EMI to efficiency to even stability as well too. So if you probe phase nice and tight, close to the FETs, you can tell a lot about your regulator.
So this should be as small as possible?
The phase node? Yeah, you want to minimize the phase node, make it no bigger than you have to.
But it still need to be able to handle the currents?
Yes. So let's see. I know from going through here, there is a layout example. Yeah, so you can see here they have their DrMOS chip, and there's just a nice short, wide phase node. So you can see here it's pretty dense. So if I were probing this, I would make sure my probe tip is as close to the package pins as I can get them, and then find ground here on one of these other components, capacitors or whatever, maybe the output cap if I had to, but it looks like these might be input caps, to couple as close as I can to the actual ground of the phase node. So if you're probing phase nice and tight, you can tell quite a bit about your system. So, we've been mentioning ringing quite a bit. So the ringing on the switch node typically is, in the hundreds of megahertz regions, for a lot of board designs, which is, right in the range of EMI issues. So you don't want phase to ring too much. Making sure you're measuring the actual ringing, not due to long ground clips and stuff, is very important. As you go through the data sheets here, I know we have one up somewhere. So you can see absolute max ratings. So on the boot node, the switch node, this other phase node here, you want to see no more than 27 volts peak. So you see, as you're on your scope, if you see all of a sudden 30 volts or 35 volts, that could be a problem. So you're over voltaging your FETs, which may not be an issue, for you just have to hit a trade show. Something has to work for a few hours for a trade show demo, but if you're trying to go to production, high volumes, that's a problem. You could have reliability issues if every switching cycle you're going volts outside of what your FETs are capable of. Sometimes you'll see in data sheets, this one doesn't do it, but I've seen it on a few. You'll see, the absolute maximum voltage is 27 volts, but then they'll say over here, DC. So that's the DC voltage that it expects to see. Other times you can see, switch node ringing, or they'll call it out like ringing somehow. They'll say 30 volts less than 10 nanoseconds or something. They'll specify it that way in a data sheet, in which case you can look at your waveform and say, okay, we're at 30 nanoseconds, but we're only at 5 nanoseconds. So technically we're within the data sheet, but I'd like a little bit more margin. But if we absolutely had to live with this, as long as I did my homework and knew, once we got this thing running at high temperatures, it's not going to fall apart, our design is safe. So yeah, look at your data sheets, make sure your peak is less than the absolute maximum called up by the data sheet. If they don't specify ringing or 10 nanoseconds or anything like that, just assume the DC level is the maximum level and try to minimize it, any ringing above that.
Yeah, ideally the ringing should not be there, correct?
Ideally, yes, phase would be a perfect square wave. Typically, there's always some ringing.
Okay.
And then it's just a matter of controlling it so you hit your EMI goals and you're not having any reliabilities with the FETs. So yeah, usually it's hard to make all the ringing go away. But yeah, if you use like a snubber circuit, you can basically get rid of it altogether if you do a properly designed snubber.
Is it going to work for all currents?
What do you mean by all currents? All load currents?
Yeah, if you use this special circuit and you will be switching, I don't know, 100 milliamps and then 5 amps, is going to still minimize the ringing same way?
Yes, and that comes into part of your snubber design too. To a first order, the ringing on the phase is ringing on the phase. It's the same no matter what the load current is. In practice, though, as the load current increases, you can see the ringing increase up to a certain point, and usually it'll kind of top out at the worst case. So if you had to go through and design a snubber or play with your gate resistors, boot resistor, you'd want to make sure you're doing it under the operating conditions that produce the worst ringing.
Okay.
But yeah, once you design the snubber, if it's designed right, it should cover it over all load currents. So yeah, so you can get ringing, EMI issues from phase. We talked about efficiency and shoot through and everything.
Okay, we can explain this. I think this is important.
Yep. So shoot through, whether or not you can see your upper and lower gate pulses, you can totally see it on the phase node. So instead of snapping up and being a nice sharp edge on phase, if you see kind of like a sharp dip down outside of any ringing, this would be kind of early on in the switching cycle. You'd see if upper gate and lower gate are on at the same time. Phase would maybe start to rise as you turn that FET on, and then there's a short, so it collapses because the end's shorted directly to ground, and then eventually lower gate turns off, and phase then rises back up to the end because upper gate's still on. It's like a sharp dip in phase, and then it continues climbing. Kind of is indicative of shoot through, which is something you definitely want to watch out for. So yeah, shoot through. If there's ever so slight, tiny amounts of shoot through, you may never notice or may survive. But it's not something I'd want to take to production. I'd want to make sure we were not shooting through on any design I put my stamp on.
Okay. So basically, you are decreasing efficiency, and also it can be dangerous for the components.
Yes. Yeah. Even if it's just, it's not enough shoot through where you have a dead short and blow something up. It's still power from the input, not going to the output. It's going straight to ground. So you're throwing away that power. You're hurting your efficiency quite a bit, depending on how much shoot through. If there's just a little bit of overlap, maybe it's less than 1%. If it's significant shoot through where you're still not blowing things up, but you're surviving, you could be single digit. Maybe, I don't know if you get to double digit percentage points without blowing anything up, but it might be possible. So if you fix your shoot through, all of a sudden you can see efficiency jump up quite a bit. And
so
then,
how do you fix this? Through that resistor?
Yes. So yeah, you can fix shoot through the boot resistor, the gate resistors, or layout spins as well. Depending on if you maxed out everything you can do on the boot resistors and the boot resistors and the gate resistors, and you still have shoot through, then there's something else going on in your system. You have to look at your controller a little more, your layout. You got to really dive in. But assuming that's all designed right, and you're just seeing a little bit enough to, you go through the app note we talked about here, and one of the things I love about this is he goes through and tells you how to calculate losses for just about everything you can think of for different FETs under different conditions. So if you go through and do something like this, and you estimate that you should have 83.6% efficiency, and then you get it on your bench and you're measuring efficiency and you're coming in at 80, well, how are we doing that? It's time to start going component by component, and looking at phase is one of the ones I would do first, and just make sure, okay, we have no shoot through, or yes, there's shoot through. We have to solve that, because even if we don't account for board losses, this and that, whatever, if we get up to 85 and call that good enough from our paper design, you don't want to have shoot through in your design, because it might not be blowing up on your bench as you validate 1, 10,
but
20
after
boards.
1 year it may.
Yeah, exactly. After 1 year, you're running 100 million products or something. There's going to be one that's worst case where everything lines up, component tolerances, the FET parameters are all on the worst case scenario, and just bam, blows up. And depending on what your application is, that can be unacceptable.
So how do you measure efficiency of your power supply?
So as you look at it, simplest way, you're looking at it on your bench. You measure your input voltage and your input current. You measure your output voltage and your output current, and it's output power divided by input power.
Okay. I just wanted to clarify this, so
Yes. Yep. Yeah. P out should equal P in. In practice, that's never actually the case, because there's losses through everything. PCB, components, packages. So yeah, your output will never be your input, but in a properly designed system, you can get pretty high efficiencies.
Okay.
Some of these multi-phase regulators, as you go ahead and add a lot of phases, even though you're switching at 400 amps, you can get 95+% efficiency.
Nice.
Do it all right. Yes, because if you're in a server room, there's how many racks of servers.
Yeah, you don't.
Yeah, you don't want to turn the place into a sauna all of a sudden, because every phase, not even every regulator itself, every phase is dissipating 10 watts. Like, that's going to get so high. Your heating and cooling costs are going to go up. Reliability goes down. Yeah, you all want all the efficiency. And then in the mobile world where I am currently, it's all about battery life. So every little milliwatt you save is just that much longer you can watch YouTube videos.
Okay, dead time.
Yep. So dead time, yeah. So one way around shoot through is to add dead time. So your upper gate shuts off, and then before lower gate turns on, there's a little bit of time where the switch node is not conducted, or none of the FETs are turned on by the gate driver. So that's called dead time. And in that case, that's when the inductor pulls current through the low side body diode before switching to either low or high. So dead time's good, prevents shoot through, but again, it's one of those things you don't want to add too much dead time, because then you're burning extra current through the low side body diode. You don't have to. Your efficiency starts to collapse again the other way and drop.
Is that the reason why sometimes you see these diodes also, like external diodes somewhere in the circuit?
Yes. So there's a few spots you can add external diodes. One would be One would be on the boot side of things. So a lot of times this boot diode is integrated, so it's in the gate driver IC itself. But you might see that Schottky diode or something put externally between the VCC pin and the boot pin. That's one place you might put a diode. And then, yeah, here as well, you could put an external Schottky diode in parallel with the lower FET or the upper FET too, if you really wanted to kind of lower the diode losses.
Mm-hmm.
But that comes down to, cost. A Schottky diode that would be lower loss than what's on the FET is a little bit pricier than a standard diode. Board area, again, it's just another component in that critical switch path you have to get placed exactly right to not cause any other problems.
Mm-hmm.
So it's depending on the system. Yeah, it's not really something done too often, and at least the motherboards I've designed.
Mm-hmm. Okay, and again, you control this dead time same way as you control the shoot through timing.
Yeah, you can, or sometimes the driver will have a dead time adjust option, or the controller they'll let you adjust the dead time. But typically, that's kind of the reason. Like the DrMOS chips we've been looking at have kind of come into fashion, is because you get a nice optimized driver and a nice optimized set of FETs, and the designers of that silicon have accounted for all the ways the FETs have shifted over process and voltage and operating conditions and how the driver shifts. And this is a tricky part of the design, and doing it all discrete. It's easy to forget something or just make too many trade-offs one way or another and kind of hurt your efficiency.
Mm-hmm.
So that's kind of why integrating the driver with the FETs, either in integrate everything, driver FETs controller, or controller then with separate driver FETs, is kind of the two most common methods of designing a buck regulator. Is this part here is very tricky to get right, and especially over all operating conditions that you might expect.
But it's good to know about this, because
yeah,
if you would like to double check the power supply, what someone created, they can measure these signals and they can be like, oh, okay, everything seems working correctly.
Yes, exactly. Yeah, it's good to double check. And if by chance you do find yourself with a controller or gate driver or something that lets you adjust the dead time on your own, being able to understand at least what you're doing is very important. So you're not just tuning it blind and then hoping for the best.
I wouldn't know what to actually measure. So everything what you are just explaining, I find it like super useful. I never went so deep inside power supplies to try to understand all those signals. So this is like super useful. What is on your next slide?
Sure. So yeah, your efficiency, your reliability, your ringing. The other one of the importance of phase is stability and jitter. So you're triggering on phase, it's on your scope. Two measurements you might do are edge and period jitter.
So this is the edge, PWM signal?
No, this is phase itself. You can look at PWM, you might not have access to it. If you have one of those integrated FET regulators like this one here, we don't have a PWM signal. So phase is usually always there unless you have a module. So that's why I'm talking about the importance of phase, because it can tell you the same thing PWM does, plus a bunch of other things.
So phase is the switching mode.
Correct. Yep. Phase and switch are interchangeable. Yeah.
Okay.
Some vendors call it switch node, some call it phase. I think I've jumped around a few times during our talk here calling it switch or phase, but it's always the same voltage.
Okay.
Same node in the circuit.
Okay. And basically this can have some jitter?
Yes. Yeah. So due to delays in the IC, different modulation. Also too, we talked about way back at some point here, voltage mode control, where depending on your error amplifier, how your error amplifier looks to a ramp signal, in a real system, it's not just a flat voltage. It's going to, bounce around because of noise or load disturbances or whatever. So your on time is going to change. So looking at phase, you can kind of get an idea of how well your control loop is doing. So for edge jitter, you're looking at how much does the on time vary. And period jitter, you're looking at, if I clock my scope at one rising edge, how much does the switching frequency vary, the period of the switching time? And that can tell you a little bit about the stability of your regulator. It goes back to knowing what kind of regulator you have. So we mentioned V squared constant on time regulators. Constant on time, it's right in the name. On time should be constant for a given set of conditions. So if you look at a constant on-time regulator and you see your on-time is jittering like crazy, based on your calculations or the data sheet, you should see 100 nanoseconds on time, but you're seeing it bounce between 50 and 200. Well, something is very wrong. Either you have to adjust your compensation, or you missed the little blurb in the data sheet that says don't use all ceramics. You need at least this much ESR for the controller to work. So that tells you to go back and check the regulator.
So basically it means the feedback loop, what you are putting back to the controller, there is something wrong with the signal in the feedback loop?
Yeah, something in your control loop isn't stable. Your poles and zeros aren't placed right. You don't have enough ESR.
And control loop is like whole around?
Yes. Yeah, so it's the whole brain. So you're picking off your output voltage, and it's feeding back to the controller to know what Vout's doing at any given time, and it's adjusting that PWM duty cycle. To
so all this is control loop?
Yes. Yeah.
Okay.
Something in your control loop is off. Again, it's knowing your modulator. So if you have a constant on-time modulator, you don't want to see a lot of on-time jitter. But that's a little wobbly when it comes to frequency, so you might see a lot of period jitter. If you have something like standard voltage mode control or peak current mode control, they show it right here on this thing we've been referencing. There's a clock that's setting your switching frequency. So if you have a clocked architecture and you go ahead and you look at phase node and you see from one period to the next, the switching frequency is varying by 20%, that could be a problem with your control loop in a clocked architecture system. Something's going on. Maybe you need more slope compensation in a current mode system. Maybe your poles and zeros aren't placed quite right for voltage mode. That's something that's a clue of, I have to go through and do a little bit of a deeper dive here. My system's not working quite right like I expect.
So as you said, maybe you can play with the capacitors, or maybe, I don't know, what is there? You need to use different transistors, or I don't know.
So we kind of not touched on the compensation loop because it's its whole other beast. But if we go to, let's see.
Basically, if it's wrong, then it means there is something really wrong.
Yes. So this is the first Google result for buck regulator compensation. So as you look, your output voltage, this is the inductor, the transformer, the power switches, whatever. You pick your output voltage sense point, you feed that back, and there's an error amplifier in your compensation network. And doing that, setting the poles and zeros of this network is what's making your output stable. So as you look at phase, you can get an idea before you go through and do your whole validation, take Bode plots, transient response, all that jazz. This is just a quick way as you're going through, there's too much jitter on one of these edges here, edge or period. That's something to look for. Maybe I have to go through and work through whatever this is, all the math here, and figure out if my poles and zeros are placed at the right place.
Wow.
And then two, it's a whole system. When you're looking at a regulator. And then as you're watching the phase over, not just one or two cycles, but multiple cycles, if you start seeing things like, a narrow pulse, a wide pulse, a narrow pulse, a wide pulse, alternating wide and narrow is also a sign of poor stability. You could have a compensation problem and, poor gain margin. So as your Bode plot crosses 0 dB, maybe it doesn't just keep rolling off. Maybe it flattens out for whatever reason. Maybe it peaks back up above 0 dB. So in either case, either it flattens out and doesn't roll off, or it peaks above 0, you have poor gain margin. And your system, while it may be stable from a phase margin perspective, if a component shifts, all of a sudden you're actually not stable. So seeing these alternating pulses on the switch node is another key that, somewhere in my larger regulator system, I have to go back and take another look at what's going on.
Okay, what is next?
Transient response. This is a big one. So your regulator isn't going to just sit there and, chug along at 1 amp. Maybe it will for some systems, but in any system really doing anything, as a microcontroller turns different pieces off and on, you toggle an IO or toggle 10 IOs or 20 IOs, or you're powering a processor and you have to crunch some video or, some encoding algorithm. All of a sudden you pull a lot of current. You have a load step, and doing that kind of stresses your regulator. And it's really easy if you don't design your regulator right to see instability and oscillation. So knowing what to look for when you see the transient response is a big one in determining if your regulator is working correctly. So when you look at your output voltage on a scope, you can see a couple different regions here during a load step. Yeah, the output voltage is switching. You hit it with a load step and the 4 regions. The first one here, all this assumes a real capacitor that has parasitic resistance, inductance, and then the PC board comes into play as well. But you can all fold it in for the purposes of this conversation of ESL, ESR, your output capacitor. So load step hits, and you'll see a nice fast spike in this first region here, and that's due to the ESL of the capacitor. And the faster the load slew is, the faster you pull current, the bigger of spike you're going to see there. And then region 2, you kind of, instead of being just a fast, almost vertical spike, it kind of looks linear. And that's due to the ESR of your output capacitor and your PC board. And then, you'll see region 3 here as that portion goes off and the inductor current is starting to slew. So your regulator control loop can only respond so fast. And when the load hits, if it's fast enough, the regulator doesn't even know that the load changed. You're at, how well did you design your inductor, your capacitor network, your PC board? That's all handled by that before the regulator takes control. And that's regions 1 and 2. And even region 3, if the inductor starts to ramp, the controller is working and doing what it can, but you can only refill the output caps so much through that inductor to keep the out in regulation. So you can see the out start to dip even more as C out discharges. And then eventually you'll recover. Your inductor current will reach the output load, but you'll still have to recharge the output capacitance. So you'll see the out kind of dip back up, and then you'll hit steady state regulation again. And that's region 4 as the inductor current hits the load current and refills C out. All of a sudden you have excess current stored in the inductor, so it can start charging the capacitors again.
And this is also somehow related to the switching frequency of the regulator?
Yes.
These times?
Yes and no. So to a first order, we said, as you design your bandwidth, how fast the controller can respond, it's to the roughly 1/10 of your switching frequency. So that's another benefit to going to a faster switching frequency, is you can set a higher loop bandwidth to respond to load transients quicker. In practice, it's not exactly true. You can push that 1/10. That's kind of the conservative. We want to make sure this design always works. We don't need bleeding edge performance. So we'll stay at 1/10 the switching frequency. But if you wanted to push things, you can get to a quarter, a third, a half of the switching frequency if you absolutely had to. And then there's also a whole ton of tricks you can play inside the modulator to do nonlinear control as well, and turn on all sorts of optional features to improve your transient response as well. But that's a whole nother topic right there.
So basically between 3 and 4, that's the time when the regulator starts detecting the change, or?
It depends on the regulator. In this case, because the inductor current is starting to slew up beforehand here during region 2 and 3, that means the controller is controlling, because the only way for the inductor to charge up is for the upper FET to be on. So you need a PWM signal. So the controller is responding and sending more current to the output.
Okay.
So if you're looking at either PWM or switch on your waveform here on your scope, what you would see is an increased on time, because you're trying to deliver more charge to the output to keep the out within regulation. So instead of seeing 10% duty cycle, or 100 nanoseconds on time, maybe you'll see 120, 130, 140, something like that. If you have a multi-phase controller, you'll start to see the phases fire faster, possibly overlap with one another, so multiple phases are on at once, trying to keep the out within regulation.
Okay. Do you have also something about multi-phase regulation? How it works?
I kind of left that out here, but I did while I was at TI write an app note about multi-phase design.
Just like a generic advantage or something?
Yeah, so this goes through here. This app note I wrote way back in the day when I was working for TI goes through the advantages of and disadvantages of multi-phase control. So you can reduce your input capacitance requirements, your output cap requirements, thermal performance and efficiency at high loads. and your overshoot and undershoot. So this transient response here is you get better performance for multi-phase versus a single phase regulator. And so, yeah, I talked about that here in this app note as well. And part of what I did at TI when I was there is I put a whole multi-phase training portal together if you wanted to learn more about it. But we could do a whole video on multi-phase, and actually I did. So yeah, these are my videos from, God, I don't even know anymore, 7 years ago? No, not 7. 5 or 6 years ago. I went ahead and did some videos when I was at TI about testing multi-phase regulators and designing and all that stuff. So it's a whole nother world.
Okay, but so basically how it works. So you have kind of multiple regulators connected in parallel.
Yes,
and
yes.
So they can deliver higher currents with components which are not rated for the maximum current which can be delivered. So they can be smaller, cheaper. But
correct, yeah.
So how does it work, this switching you just mentioned? Because this is interesting. So they don't switch all at the same time. They switch.
Yeah,
how?
So you'll see it staggered. Yeah, if you had a multi-phase system and you were looking at phase 1, 2, and 3, and it was in steady state, you would see the first switch node fire, and then the second switch node fire, and the third switch node fire. They're kind of offset in time. So at any given time, one of them is usually on, and then you cycle back from phase 1 to 2 to 3, back up. In this case, it's a 3-phase example here: 1, 2, 3, 1, 2, 3. If you went all the way up to 8 phases.
So it's like basically if you would have one regulator with triple frequency. So it would be like much faster.
Yeah, the effective switching frequency is 3 megahertz instead of 1 or whatever it is.
So basically the output voltage can be even smoother.
Correct.
Because the regulator can react much faster.
Yep. Yeah, there's less ripple on the output. In the transient response, because you can kind of turn these phases, I guess I'll just stay here, it's the best example. You can turn these phases off and on more quickly, and you can overlap. So instead of having one inductor that limits how much charge you can put to the output, all these inductors are the same value. So you have, in this case, inductance divided by 3. Now you can deliver charge 3 times faster to the output during a transient response. So you get less overshoot, less undershoot, things like that. So yeah, your performance goes up there. And it's not always, I will say, high power for multi-phase. In some of the cell phone chips I've worked on, just because of the sheer size of things, you go to multi-phase, because even finding an inductor that can handle 15 amps, which is something we can go and find 100 million examples on DigiKey for. If you're trying to fit that in a cell phone, it doesn't fit. So you have to go to such small inductors that you go to a multi-phase design, and all of a sudden you have to find inductors that can handle 3 amps. And you do a 5-phase design, and that kind of dictates one of your designs there. It's a whole interesting world. You see it either on the super low end where you can't find big parts, or the high end where there's a lot of power.
And you mentioned this phase, it can even like overlap, or this phase can be
during a transient response, it's possible.
Okay.
Yeah, it depends on the controller. Sometimes you can turn them on, sometimes you can't. Sometimes it's an option. So you can have phase overlap or not phase overlap. In general, though, I would say as you're designing your system, if you have any of these fancy nonlinear control features of like phase overlap or diode breaking is another one, turn them off to start with. Make sure your system works before you go ahead and say, okay, we've compensated the regulator as best we can. We've optimized the output capacitance, the inductance. There's still just that little bit of performance we need. Then go ahead and start turning on any features like that. Because if your system doesn't work right to begin with, all those nonlinear things, in my experience, have kind of they make it worse. They can make a good system perform excellent, but they can't make a bad system work.
Thank you so much, Carmen.
Thank you for having me on too. This was a lot of fun. We could probably go another couple hours if we had to.
Yeah, this was super interesting, because for me, power supplies are usually just like small part of a board, and I don't really spend much time, playing with it. So it's like super useful to finally be able to talk about these signals which are in the power supplies and understand how they look, what they do, how they are generated. So like, thank you so much.
Yes, thank you. And yeah, for anyone listening or watching or whatever, any one of these topics we touched on today could be its own video or series of videos. I mean, Ridley Engineering has 100 videos just on current mode control, it seems. So it's a very deep topic. So use this as a jumping off point to go and Google whatever you need to get your design up and running.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FETs online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.